Okay, let's start talking about temperature. And you might think, haven't we been talking about temperature? Well, sort of almost. We've been talking about heat. The first thing you need to understand about temperature is it's not the same thing as heat. Sometimes people think temperature is just another word for heat. Some people say a little more detailed temperature. Some people think temperature is a measure of how hot or cold something is. And again, we want to get away from those words hot and cold for the most part because they're relative terms. So if temperature is simply a measure of how hot or cold something is, then I can simply use myself and just go outside and say, oh, it's hot or it's cold, and I don't need a thermometer. But temperature is more than that. It's important to understand that temperature is, and focus on this definition for a second, it's a measure of the average kinetic energy of the molecules of a substance. Temperature fundamentally is a measure of energy, and specifically the average kinetic energy. We're talking about moving energy. Kinetic energy is moving energy because the molecules are vibrating, as we said before. So, temperature is a measure of the average moving energy of each of those little molecules. Now, let's talk about the word average. We only use the concept of average with things that are not all the same. For instance, I could ask you, what is the average number of legs of the people in your class? And that would be a silly question because more than likely, everybody in your class has two legs. And so they're all the same. There's no reason to calculate an average because the average is two. However, if I asked you, what did your class make on the test? That would be a more difficult question because everybody made a different grade. But what I could do is give you the average, and that would give you a little more information. So, the first thing to understand about this concept, the reason why we use the word average here, is that not all molecules have the same amount of kinetic energy at the same time. Let's take a look at a graph. On the y-axis, the vertical axis of this graph, we have the number of molecules at a particular kinetic energy, which is on the x-axis. And so the red line represents a warmer sample, perhaps our cup of coffee. The blue line represents a cooler sample, perhaps our cup of soda. And so there's a couple of things that should be fairly obvious that I want you to understand here. The first of which is the molecules don't all have the same kinetic energy at the same time, which is what I said before. In the cup of coffee, some of these molecules have really high kinetic energy, but some molecules have really low kinetic energy. Same with the cold sample. Higher kinetic energy, lower. Now we see the cold sample, the higher kinetic energy kind of falls off much at a much lower energy than the higher does. But they don't all have the same amount of kinetic energy at the same time. Some molecules, by random chance, will have more kinetic energy. Some, by random chance, will have less kinetic energy. And there's a lot of reasons for that. One of which is they're always bumping into each other and transferring their momentum and energy. So one molecule might lose energy while the other one gains it. And then that process keeps happening. But the important thing to see here is that the average kinetic energy is the kinetic energy in the middle, where you can see most of the molecules in this cup of coffee have an amount of kinetic energy that is around this area. And most of the molecules in the soda have an average kinetic energy that is around this area. And so that average is different. It is higher for the warmer sample. That indicates temperature. So when we say temperature, we're talking about an overall average amount of kinetic energy for the molecules in that substance. Now, we said earlier that this temperature depends or determines, rather, temperature determines how fast these molecules are vibrating. So these molecules are vibrating faster, these molecules are vibrating slower. Um, and let's imagine what happens when we decrease that temperature. We saw earlier as the temperature decreases, then the molecules vibrate slower. And the molecules, as they're vibrating slower, they will have less kinetic energy. Well, what happens if we just keep decreasing that temperature? Well, probably not surprisingly, that kinetic energy will keep going down and keep going down and keep going down. And you can probably figure out by now that at some point, that molecular motion must stop. And that point is called absolute zero. You may have heard about absolute zero before, and this is what it is. Absolute zero is when all molecular motion ceases. Couple of questions about absolute zero. First is, can you have a temperature below absolute zero? Some people think the answer to that question is yes, because they think, well, I've seen negative Celsius temperatures, but that's not the same thing, because 0 Celsius is not absolute zero. You actually cannot have a temperature below absolute zero. And the reason for this is, well, if all molecular motion has ceased, then you can't go any slower than that. You can't take any more energy out of an object that has been depleted of its energy. So there is no temperature below absolute zero. That's why it's called absolute zero. That is the absolute bottom for temperature. And the second question about absolute zero, can we actually reach it? And the answer is no. We've already learned about the second law, which says that heat spontaneously flows from hot to cold. So it doesn't take too much imagination to figure out that once you reach or even get close to absolute zero, that will be the coldest place in the universe. There's nowhere in the universe at absolute zero. And the colder you get, the more likely it will be that something around that object will be warmer, which means heat will flow from that warmer object into the object approaching absolute zero, which will further increase its temperature. Long story short, that makes it absolutely impossible to get all the way to absolute zero. We've gotten really close, within a billionth of a degree Kelvin, and we'll talk about temperature scales in a little bit, but we can't actually get all the way to absolute zero.